Hey there, this is Mr. Boyce, and I am starting this video by showing you the answer key. What I'd like for you to do is to go through, and if you haven't done this yet, just stop this video and do the review. Treat it like a test. Use only your calculator and your periodic table and formula sheet. Uh, don't use any notes. See how you would have done if this was a test. And then come back, go through this answer key, and see how you did. And that way, instead of watching this entire hour-long video, you can kind of skip to what you need. See that question number 2 with the red thing on it? That is a very important one. Make sure that you catch that one. Also, just under it, question number 6 is another one that can be a bit tricky. So no matter what, make sure you listen to those two. But other than that, most people won't have to watch the whole video, but it would definitely be helpful. And so I hope you enjoy it. It is kind of long, but hopefully it's very helpful for you. So without further ado, let's get into the review. Hey guys, this is Mr. Boyce, and we are going to go through and do our review for our Unit 1 and 2 test. First off, what do you need to study? Your binder assignments, your homework, your notes, and your density lab. This question will have multiple choice, short answer, and will require calculations and quite a bit of conversions. So let's start off with some of the quicker questions. First off, who discovered the center of the atom was very small and dense with an overall positive charge in his gold foil experiment? And this was Ernest Rutherford. And we're going to talk a little bit about more him later. Okay, the blank is always equal to the number of protons plus the number of neutrons an atom has, and that is the mass number, not to be confused with the atomic mass, which is the weighted average of all of the isotopes. An atom that gains an electron will have what type of charge? Well, electrons are negatively charged, so if you gain electrons, you are going to be negatively charged. The blank of an element is the weighted average of the masses of the different isotopes, and that is the average atomic mass. The atomic number of an atom is always equal to the number of protons, which you can abbreviate with P and a little plus sign. Thomson discovered the blank in his cathode ray experiment. He discovered the electron, which you can abbreviate as E and a little minus sign. Blank are atoms that have the same atomic number, but different mass numbers. So the number of protons can never change. That is what defines what something is. But the number of neutrons can vary in between atoms, which will make it weigh a little more, and those are called isotopes. So isotopes is in the same, but a bit different when it comes to weight. An anion is an atom with an overall what type of charge? Well, if you remember, cats have paws, and so cations are positive and anions are negative. An atom gets its overall positive charge by gaining or losing electrons. And in this case, if your overall charge is positive, that must mean you have more protons than you do electrons. So therefore, you are losing electrons, which is going to cause you to be overall positive. So how did Thomson know that the charge of the particle he discovered was negative? Well, what he did was he had a ray tube. and it had all the different rays going through there, and he had a positive. Let's change the color, make it look a little more obvious. And on the bottom, he had a plate, and that plate had positive charges, and opposites attract, positive attracts negative. And what happened was some of those were being angled downwards towards, attracted towards the positive plate, which showed that they were in fact negative. Rutherford's gold experiment. Now, this one's actually really interesting. Here's what happened with this experiment. First off, we had a detector. And this detector was kind of a big semicircle sort of thing. Right? And then we had, let's see, can I do gold as a color? That would be so cool. Let's see. Can't. And so we had a tiny little bit of gold foil, very, very, very thin gold foil. Gold is extremely malleable. You can hammer that into just barely over an atom thick. And so what they did was they took a radioactive source. So let's see if we can draw a radioactive source. Let's see how artistic I am. Not bad. And what they did was they shot at that foil. Now, at the time, what we thought atoms looked like was what's called the plum pudding model. And the plum pudding model would basically be, we thought an atom would just basically have positive and negative charges kind of on the outside of it. And so kind of plum pudding, bit of an outdated, we don't really eat that anymore, but think of it maybe like a chocolate chip cookie where all the chips are kind of on the outside, your positive and negative charges are just kind of all there. But the important part is they basically thought that the atom was pretty consistent in its density. So if you're shooting these alpha rays from a radioactive source, what you would expect is that it would just fly right through this tiny piece of gold foil, like shooting a bazooka through a tissue paper or something. But what actually happened was some of these rays would, of course, go straight through like expected, but some of them would be deflected a bit, here and there, and they would just kind of hit around, but still kind of go forward. But what really surprised them was some of them would get shot just straight backwards. And that's not something they expected would happen. And so what that showed was that an atom is actually a very small, dense center with electrons just kind of floating all around it. And this is kind of more the picture of the atom that we're used to seeing. And so that's how they discovered that there was, in fact, a nucleus. Okay, an element has two common isotopes. First isotope has a mass of 68.926 AMU and occurs 60.10% of the time. The second isotope has a mass of 70.925 and occurs 39.9% of the time. And what I want to do is find the average atomic mass. This is sort of like taking a grade point average. And so 60% of my atoms are going to weigh 68.926, and 39.9% are going to weigh 70.925. So in my calculator, what I'm going to do is I'm going to type in 68.926 times, and then 60.10. I can do 68.926 times 60.10, but then I would have to divide it by 100. But it's kind of a lot easier to just go ahead and change 60% into a decimal. You're going to move that 1, 2 places, and that comes out to 6010. And that's only one of the two, so I need to add that to my second isotope, which has a weight of 70.925 AMU and occurs 39.90%. So converting that into a decimal, I'm going to do 0.3990. And if I put that into my calculator, it's going to give me an answer of 69.72. Now, the highest number I have is 70.925, and the smallest is 68.925. So if I take an average of those numbers, regardless of what the percentages are, it's going to have to be more than 68.926, and it's going to have to be less than 70.925. And since 60%, the larger amount, is in the 68.9, I'm going to expect my average to be a little bit closer to the 68.9. And that's what I have. I have 69.72, which is right about in the middle. So this makes sense. And that's my answer. Okay, let's fill in this element symbol chart thing here. Okay. First off, well, apparently, let me just tell you right now, converting this from Microsoft Word to Notability here erase some stuff. So on your printed form, you're going to see a little bit more than what's up here right now. And one of the things pre-written in here is 2914 I. Okay, a little hard to answer it without knowing that. Okay, and then cobalt is as it is, and this should have BR -1 of 80 and 35. And I'm pretty sure that's it. Okay. So starting with this is what you're going to see on your page. We're going to figure out what's there. Now, I like to call this the Big Mac. In other words, you have your big symbol in the middle, the BR here, and then Mac, M-A-C, that's your Big Mac. So on the top here, you have your mass number, which we know is the sum of the protons and the neutrons. We also have our A for the Big Mac, and that's 35. That is your atomic number. Atomic number is the number of protons. And then finally, C for charge. In this case, the charge is a -1. Okay, so atomic number. Well, that's a pretty easy one because this is your atomic number right here. So I can put in a 14 for the atomic number. Let me go ahead and put that in there. And the atomic number and the number of protons is always the same number. So I can just kind of fly right over there and put that on, right? And in the Big Mac, conveniently, this right here is my mass number. So I'm going to go ahead and put 29. And then the last thing I need to know, or well, two more things, the number of neutrons, and the mass number is the number of protons and neutrons combined. And so the number of protons can never change. If I have this particular element, which is silicon, then I have to have 14 protons. 29 minus 14 is 15. And so therefore, that's how many neutrons I have is 15. 15 plus 14 equals 29. So we're good. Number of electrons. This has no charge on it. And so therefore, the number of protons, which are positively charged, and the number of electrons, which are negatively charged, match each other, which is why there is no charge. So if I have 14 protons, I must have 14 electrons. Okay, next. So you don't have the element symbol, but you do have the number 23 for a atomic number. In 23, there's only one element in the world that can have a 23, and that's right there. That has 23 protons, and that is vanadium. I'm not actually sure how to pronounce that, but it's a B. Right? And now Big Mac, so I already know what my atomic number is, so let's go ahead and put a 23 there. And my mass number is 51, that's nice. 51, let's put that there. And let's see what else is going on here. Atomic number is 23, so therefore the number of protons must be 23. And the number of neutrons would be 51 minus 23, which would be 28. And the number of electrons is 23, but my number of protons is 23 as well. And so therefore this is going to have no charge. And so I can leave it just like this. Okay, element symbol CO. Let's find out how many protons are in that particular element. Zoom out a little bit here. And let's go and find that cobalt. Where are you hiding? Oh, there we go. Cobalt. In the transition metals in the D block, cobalt has got 27 protons and a mass number of approximately 59, but let's go ahead and see what the chart says. 27. So the atomic number from the periodic table is 27. And if the atomic number is 27, we know that the number of protons is 27. And 59 minus 27 is 32. So we're squared away on the number of neutrons. Now, electrons is pre-filled in for me. There's 24 electrons. But wait, I've got 27 protons, which means I have more positive than I do negative. In fact, I have 3 more. So my charge here is going to be a +3. And let's fill in the Big Mac. So my mass number is 59, not the best 5 ever. Let's make it a little better. 59. And my atomic number is 27. And so the Big Mac is filled in. So this last one, we're going to take the Big Mac and figure everything else out. First off, we know 80 over 35 BR minus 1. Okay. So 35 is the atomic number, and therefore the number of protons. Okay. 80 is my mass number, because that's what that means. And the number of neutrons is going to be 80 minus 35, which is 45. And this has a -1 charge, which means it has to have at least one, or at least exactly one more electron than it does protons. So if it has 35 protons, that would mean it has 36 electrons, therefore a -1 charge. And we're done. Okay, group 1 is known as the alkali metals. And that is right here. This is group 1. Now remember, hydrogen is not a metal. Hydrogen is kind of like the weird exception to everything. More than like, I would say the best reason for it to be where it is because it forms a +1 charge also along with the alkali metals, meaning that it loses an electron. And that charge is very important, so very good reason for it to be there. Okay, the 2 rows on the bottom of the periodic table are also known as the what? Those are known as, whoops, I just went right back to the same page. That's not helpful. All right, so right here, see if we can get a little color in there. This is your S block. This is your P block. P, actually. And when we get into electron configurations, we'll explain that helium is actually part of the S block, but let's not worry about that for now. So this is your P, S. Transition metals are the D, and down here is the F block. An atom with a positive or negative charge is called an ion. So you can go further and call them a cation or an anion, but the general word is ion. It becomes charged when it gains or loses electrons. The atom, the size of an atom is mainly due to the number of occupied energy levels. And to give you a sort of an example of just how much the energy levels in electrons contribute to the radius of an atom, if you were to take a football stadium and scale it to the size of an atom, the nucleus would be right around in the center of the football stadium, and the nucleus would be about the size of a pea, and the entire football stadium would be an atom. So the nucleus takes up a very, very small amount of space, but it represents almost all of the density, like 99.999% of the actual weight or AMUs of an atom. Okay, so as I move across the period from left to right, the size of an atom will decrease. This is due to the increased number of protons. So what's happening here? Let's erase all that. These are my energy levels right here. 1, 2, 3, 4, 5, 6, 7. And we will get more into that as to how that relates to the SP and D block. But for the general course of this one here, let's just say I'm in the third energy level right here. That means I have my nucleus and I have 2, 3. Oh, that's terrible looking. Three energy levels. And so my electrons on the outside are further away from the center positive nucleus. And as I move down, you keep adding more and more of those energy levels. Now, what's happening is as I move from here to here, to here, to here, to here, to here, and keep going down this row, I am adding, each element has increasingly more protons, but they still have the same amount of energy levels. So the stronger the center gets, the more it's able to pull in these outer electrons and then reduce the size of the element. Now, once I get down to the very end here, argon, once I get to 19 protons, now I add a whole nother energy level, which makes it a lot bigger, and I start the process over of going left to right and causing that to kind of shrink in again. Ionization energy will increase as you move left to right. And decrease as you move down. So ionization energy is the amount of energy required to move the outermost electron. And so francium here, this is basically a trend here, but francium here, this has got all 7 energy levels. So it's huge, it's huge. It's got a lot of rings. And it only has 1 valence electron It's so far away from it, it can barely hold on to that electron as it starts. And so the amount of energy needed to remove its outer electron is going to be very low. And that is opposed to fluorine over here. It's not a very easy to read arrow, is it? Let's do that. Now this has only got 9 protons, but it has only 2 energy levels. And so its protons are just right there, so much closer. And it can see it, and there's like 7 of them. 2, 3, 4, 5, 6, 7 of them. And it wants 8, but it has 7. And so it's got a lot of control on those outer electrons. It can really hold on to them. And so the amount of energy to remove an electron is going to be very high, which is why they generally are not losing electrons or gaining electrons. This is why these form -1 ions, these form -2, these form -3. The size of a negative ion is always larger than the size of a neutral. And remember, electrons have basically no mass. So this really what it is you have all of these negative charges, and negative charges are always trying to get as far away from each other as they can. So if I only had 3, you'd have maybe one up here, one down here, one down here. If I had 4, they're going to come to the poles. And so what that's called is electron repulsion or energy repulsion. Negative charges are pushing each other away because like charges repel each other. And that's what causes the atom to get bigger. The actual mass of an electron is pretty negligible. Okay, electronegativity is the ability of an atom to attract electrons. So basically the same school of thought with ionization energy, only going the exact opposite way. So if francium here is so big and has so many energy levels that it can barely even hold on to its outermost electron, well, it's certainly not attracting more of them. Where francium over here has already got 7 out of 8 valence electrons. It is ready, it is small, it is powerful, it is right there next to its outer electrons, and so it is going to attract electrons much stronger. Now, chlorine will also form a -1, but it's got another energy level in its way in its quest to get that electron. Bromine, same thing. It wants that 1 extra electron, but it's got a few energy levels in the way that the fluorine doesn't have to deal with, and so it's not going to have as strong of an attraction as fluorine. So for electronegativity, you have the exact opposite of ionization energy. And so electronegativity is going to go that way. Okay, circle the atom with the larger atomic radius. So let's just kind of remember some of these right now. I'm going to take a look here. First off, magnesium or calcium. Okay, and that is going to be calcium. Nitrogen, or here we go, and aluminum. So let's take a look at these on the periodic table. First, magnesium and calcium. Okay. Let's clean this up a little bit so we can see what we're doing again. Okay. First thing I'm going to do is I'm going to look at magnesium, and then I'm going to look at calcium. Okay, now which one is bigger? Well, it's going to be calcium because calcium has 4 energy levels, magnesium only has 3. The next one was nitrogen, and let's see here on my periodic table, arsenic. So between arsenic and nitrogen, which one's going to be bigger? Well, arsenic, because arsenic has 4 energy levels and nitrogen has only 2. So nitrogen is going to be considerably
Oh, sorry, other way around. Rewind. Womp, 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 womp. Which one's going to be larger between nitrogen and arsenic? Arsenic is going to be considerably larger because it has 4 energy levels, where nitrogen has only 2 energy levels. And so therefore nitrogen is going to be smaller. So arsenic is going to be the larger one, which is why we circled that. Aluminum versus chlorine. Let's see here. Here's aluminum and here's chlorine. And so in this case, they both have 3 energy levels. They're both in the same place, but chlorine has got 17 protons and aluminum's only got 13. And so that stronger charge in chlorine is pulling in those outer valence electrons towards the nucleus, which is going to make chlorine smaller, and therefore aluminum will be larger. Okay. For the next 3, we're going with atomic radius, and here we have AR and O. These are going to be, let's just stay consistent here. Okay. And we're going to look at the periodic table for all 3 of these instead of switching back and forth every time and making you dizzy. We're just going to do it like this way, one at a time. Okay. And so the first thing I want to look at is right here. I've got Ga, and I'm comparing this to bromine, and bromine is right here. And so we know that gallium, number 31, since they're on the same period, gallium has only 31 protons, bromine has 35 protons, so bromine is going to be smaller, and gallium is going to have the larger atomic radius. Rubidium and strontium. So here is rubidium, and here is strontium right next to it. So they're going to be pretty close in size, but rubidium is going to be a little bit bigger because it doesn't have as many protons pulling in that outer level. And then oxygen, which is right here, that's an element you're going to see a lot. Okay, and tellurium right here below it. So which one's going to be bigger between these 2? That's going to be tellurium because it is lower on the periodic table and therefore has more energy levels. So that is going to be our larger element. Circle the atom or ion that is larger. If I add another electron, then what I'm doing is I'm adding to that electron repulsion and I'm making it larger. So the larger of these 2 is going to be the one with the negative charge and more electrons. Along the same train of thought, Mg plus 2, magnesium, that means that this lost 2 electrons, and therefore it's going to be smaller than normal magnesium. And here we are, Cr plus 3 and Cr plus 2. If they're more positive than negative, that means that this bad boy lost 3 electrons and this one only lost 2, and therefore this one is going to be larger. And I have a -3 and a -1. -3 right there, sorry, right here, and a -1, and therefore the -3 gained 3 extra electrons, and therefore that's going to be my larger one. Let's just clean this up a little bit so our answer key makes more sense. A larger electronegativity. So I've got boron, and weird, it's formatted a little different on your form. This here, so this question is actually right here on your form, but whatever, still the same question. So which one has the largest negativity between boron and Ln here? I'm going to go ahead and circle that answer. And between carbon and fluorine, I'm going to circle that answer. So let's look at electronegativity. Electronegativity is your ability to attract electrons. So the smaller you are, the more you can attract electrons, the more powerful you are. Okay. And between boron, which is right here, and where are you hiding? indium. So boron has got fewer energy levels, which is going to make boron much smaller, and therefore boron is going to be more electronegative. So electronegativity, you start at your very least right here, and you go to your highest electronegativity, which is fluorine, which is at 4.0. So that's as high as you can get with electronegativity. The next one was showing carbon and fluorine. Let's take a look at those. Okay, and here is carbon. Lovely carbon. We use it all the time. And fluorine, there's not really a match here. Which one's more electronegative? Fluorine beats everything. So there you go. If you know that, you don't even have to think about what the other one is. But here we go. Fluorine is definitely smaller. Rubidium versus cesium. Let's take a look at those. Those are the next questions on there. So here's rubidium, 5 energy levels, hardly any protons. This is pretty big. It's pretty big, but cesium is one below. It's even bigger, which means it's going to have even less electronegativity. And therefore, our answer, our winner for the more electronegative is rubidium. SN versus SB. Let's clean this up a little bit. Okay. Trouble with the pen there. Okay. Here's one. Yeah, tin versus antimony. And in this case, we want to know which one is more electronegative. And the trend for electronegativity is going to go this way. And so I am going to give the win to antimony over tin. Okay. Oh, all right. A little bit more than halfway through. This is a pretty long one, but hopefully you're sticking with me. Calculate the atomic mass of oxygen if 3 common isotopes of oxygen have masses of 15.995 at 99.759 abundance. That's a huge abundance. So let's put this in our calculator and see what happens. I'm going to do 15.995 times, and I'm going to turn this into a decimal. So 1, 2 places, and that's going to be, shrink for me, times 0.99759 plus, I'm going to put my other ones in here. That's going to be in my calculator, 16.995. And I am going to convert, let's see here, 16.995 AMU. And a tiny, tiny, tiny percent is 0.037. 0.037. And if I move this decimal places 1, 2, I have another 0, so it's going to be 0.00037. Well, that's not going to have very much effect at all, is it? Plus 17.999 times 0.02412. So I'm going to add 0.00204. Okay. And if I put in a calculator exactly the way I wrote it, the calculator is not going to give me a whole lot of rounding errors, which is important on this one because the answer is 15.999 AMU. And let's see here. So 99 points, almost 8%. So almost 99.8% is at 15.995. I take into account the heavier isotopes, but there's very few of them. And so my average atomic mass is pretty much 4 thousandths of an AMU off from my most common isotope. But this number is between my largest and my smallest numbers, and it's close to my smallest number because that's almost all of it. Okay, now this one you really want to pay attention to. This, you're going to kind of think about this in a different way. Lithium has an atomic mass of 6.941 AMU. Lithium has two common isotopes. The one isotope has a mass of 6.015 AMU and an abundance of 7.49%. Notice we didn't tell you what the other one is because they're asking what is the abundance of the other isotope. Well, the total has to be 100%, right? And so 100% minus 7.49, which we can already account for because we have that one. So 100 minus 7.49 is 92.51. And so that's the abundance of the second isotope. Now, what's the mass of the other isotope? We're going to have to do a little work here. Now, we know that the overall average atomic mass is 6.941. So let's write this out as a problem. 6.941 AMU equals, and this equals our weighted atomic average. And so I'm going to do what I know, and that is the 6.015 with an abundance of 7.49. So equals 6.015 times, and I'm going to convert 7.49 to a decimal, so 0.0749 plus, now I have my percentage, but I'm not sure yet what this is. So X times 0.9251. And so now what I need to do is solve for X. So first thing to do is a little bit easiest way to look at this is I'm going to solve for what I know. Okay. And if I had several of these, I would solve for those two. But 6.015 times 0.0749 comes out to 0.4505. Okay. Plus, and now, let's see this. And we're just going to call this, for now, we're going to call this X, because I don't know what that is. But I really should have, just to make it easier, put this over here. Let's just put that over there. Why not? Equals. Okay. Same thing, just other side makes it kind of make more sense. Plus X equals 6.941. So 0.4505 plus X equals 6.941. So 6.941 minus 0.0505 equals 6.4905. So X equals 6.4905 AMU. So 92.51% of my average atomic mass is composed of an isotope that weighs 6.4905 AMU, and that makes sense because my average AMU is 6.941, which is just a little bit more, and that's because I have just a little bit of that lighter isotope in there, and so that's what brings it down a little bit. So make sure you understand how to do this. If I had more than one isotope, I would just simply figure out, say, whatever number here, X plus this plus equals 0. Just figure out what all of these answers are, add those up, subtract it from your answer, and you're good to go. Okay, convert 5.2 centimeters of magnesium into millimeters of magnesium. So start with what you know, 5.2 centimeters. And what I want is millimeters. Okay. So the first thing I'm gonna do is bring my unit down like always. Now I can't go from centimeters straight to millimeters. Technically you can, but I don't have that memorized. So you got to go to the base unit. Okay. And notice I'm not putting numbers yet because I'm kind of coming up with a plan here. So whatever goes up must go down. I'm going to bring meters down and I want millimeters, and I can go directly to that. Meter is bigger than centimeters. So I'm going to put the 1 there, and there's 100 centimeters, centi, century, 100, and a meter. And millimeter versus meter, meter is bigger, and a millimeter is 1/1000th of a meter. So in my calculator, I'm going to put 5.2 divided by 100 times 1,000, and that's going to come up to 52 meters are on top and bottom, so they cancel. Centimeters are on top and bottom, so they cancel. I'm left with millimeters, which is exactly what I wanted. So perfect. Convert 150 centimeters of copper wire into decameters of copper wire. So again, I'm going to have to go to my base unit. So I'm going to start with what I know. That's 150 centimeters. I'm going to bring my unit down, centimeters to meters. And then I'm going to bring my unit down again because I have it meters, but I don't want it meters. I want it in decameters. So decameters. A meter is bigger than a centimeter. It gets the 1. There's 100 centimeters per meter between a decameter and a meter. A meter is bigger, and deca is in decade. 10. So 150 divided by 100 times 10 equals 15 decameters. How many millimeters are in 1 kilometer? Quite a bit, I'll bet. Millimeter is really tiny and kilometer is really huge. So let's figure out exactly what it is. So 1 kilometer. Let's take kilometer and bring it down. Can't go straight to millimeter, so let's just go to meter. Now I'm going to convert meter to millimeter. K is in, like, if a car costs 5K, it costs 5,000, right? And so kilometers bigger. I'm going to put the 1 there, and there's 1,000 meters in each kilometer. And meter versus millimeter, meter is bigger, so I'm going to give that the 1, and milli also means 1,000, just a smaller one. And so I always know what unit to put on the top or the bottom because you always bring your unit down. That's how you do conversions. So 1 times 1,000 times 1,000 again is going to be equal to 1 million. Okay, or if you want to write it a little easier, you can take 1, 2, 3, 4, 5, 6 and call this 1 times, oops, one times 10 to the 6th power. And that is going to be in millimeters. Very important to always write your units. How many inches squares are in 1 acre? Okay, if you're getting tired, come up. You definitely want to pay attention to this one. This is very important. It's a very important math rule that we're going to talk about right here. Okay, so really important. Look at this one, and this one. Very important. How many inches square are in 1 acre? An acre is equal to 43,560 square feet. So I have 1 acre. Let's go back to a nicer, a little less angry color here. 1 acre. So I have it in acres, but I don't want it in acres, so I'm going to bring that down. And I've already been given a conversion unit right here, which is awesome. I don't have to memorize this. So 1 acre is equal to 43,560 square feet. Okay, so I have it in square feet, but I don't want it in square feet. I want it in square inches. Okay. And so I know if I take feet, I know how many inches are in a feet, right? But I don't just have an inch. I have, or foot, sorry, I have square feet, right? And so if I want to convert feet to inches, but I want to convert square feet to square inches, as long as I do the same things on both sides, I'm fine. So I know there's 12 inches in 1 foot. This foot is square, so I'm going to square both of these. Okay. And 1 squared is just 1, right? But 12 squared is 12 times 12, which equals 144. All right. And so when I do my math, what I don't want to do is I don't want to do 1 times 43,560 times 12. I don't want to do that. What I want to do is 1 times 43,560 times 12 squared, or 144. Now, if I put that into my calculator, I'm going to come up with, and this is very important too, is I'm going to come up with an answer of 6,272,640 square feet. However, remember with sig figs, our rules with sig figs, conversion factors don't count when it comes to sig figs. And so literally, I've only got 1 significant figure in my math here, multiplying, dividing. That means my answer can only be to 1 sig fig. And so my answer is actually going to be 1, 2, 3, 4, 5, 6. My answer is going to be 6.0, or not even 0.0, because that would be another sig fig. So 6 times 10 to the 6th power. Okay. And that's just one of those rules. So there's my answer. Oops, not quite my answer yet. Now it's my answer. Mercury is poured into a graduated cylinder that holds exactly 22.5 milliliters. The mercury is used to fill the cylinder. Weighs 306.0 grams. From this information, calculate density. All right, so density equals mass over volume. More specifically, density equals grams over milliliters. And very, very important, don't forget, when it comes to water, at least, a milliliter of water is equal to a cubic centimeter. So these are equal to each other when it comes to water. Okay. So I have my volume right here. Here's my volume. And I have my mass. So this is a pretty easy one. It's just going to be mass divided by volume. So I'm going to do 306 grams, or sorry, 0 grams divided by my volume of 22.5 milliliters. And if I type that in my calculator, I'm going to get 13.6 grams per milliliter. I'm good on sig figs because this has 3 sig figs, this has 4, so I'm going to choose 3. So 13.6 grams per milliliter is my density. Okay, density of graphite is 2.1 grams per centimeter cubed. If I have 216 centimeters cubed, how many grams do I have? Okay, so density equals mass over volume. Okay, and so I have density and I have volume. But what I don't have is grams. Okay. And grams or mass. So that's what I need is my mass. To solve for mass, it's going to be density times volume. If you ever forget on how to do that, you can make your little triangle here. So density, mass, volume, and it's a little hard to show you that on a screen, but whatever it is I want to solve for, I cover it up, right? And so this case, I want to solve for mass. So if I cover that up, I'm left with density times volume. If I were to cover up volume, it would be mass divided by density. If I covered up density, it's mass divided by volume. Okay. So in this case, if I'm solving for mass, I'm going to do density times volume. I don't need to convert anything because it's already in CM3. So that's good. So density is 2.1 grams over CM3 times 216 CM3. And that's going to come out to 453.6 grams. Okay, and that is how many grams I have. Okay. If I have 3.3985 times 10 to the fourth centimeters of oxygen with a mass of 54.2 grams, what is the density? Density equals mass over volume. So 45.2 grams divided by 3.3985 times 10 to the fourth. And make sure, do this one in your calculator and make sure you come up with the same answer I do. If you don't, then you might not be putting scientific notation properly into your calculator. And you should come up with 1.33 times 10 to the negative 3. And that would be in grams over CM3. So this is your density. Good. All right, calculate density of sulfuric acid if 35.4 milliliters of the acid weighs 0.065 kilograms. Now, don't forget, density is grams over milliliters, not kilograms. And so the first thing I need to do is convert that unit. Always look for unit conversions. So 0.065 kilograms. I'm going to bring down kilograms and convert that to grams, which is what I need. Kilograms bigger, so I'm going to give that a 1. And a K is 1,000, so there's 1,000. So 0.065 times 1,000 is 65. Or the easier way to do it is just move the decimal place over 3. But my answer equals 65 grams for my mass. And my volume is already in milliliters, so that's nice, 35.4 milliliters. And therefore, my final density is 1.8 grams over milliliters. And that is a reasonable density, especially for a gas. Or I'm sorry, an acid, liquid. Okay. Oh, so close to being done. We're almost there. I'm glad you're still with me. Wow, how long have we been going? I'm not sure, but quite a while. Okay. 25.5 grams of iron are added to a graduated cylinder. So this graduated cylinder already has 45.5 milliliters. in it. Okay. And we add our iron to it, and this water level rises from 45.5 to 49.10 milliliters. Remember, what we care about is the liquid displacement. The water, there had to be something there for it to move in the first place, but all you care about is how much the material made the water move. Again, don't forget, a milliliter of water is the same as a cubic centimeter of volume for water. Whoops. 3. Okay, so 49.10 milliliters is where we ended up. Subtract from that where we started at 45.5 milliliters, and we have 3.6 milliliters. So this is our volume. Okay, it's mass over volume, and we already know it's 28.5 grams. So therefore, 28.5 grams divided by 3.6 milliliters is going to give 7.92. Oops. 7.92 grams over milliliters. And so there is our final answer to our final math question. Okay. Gold ring. Microscopic examination reveals no interfaces between the different types of material, which in other words means that it's all blended and all looks uniform. Jeweler's strength of 14K reports an alloy composition that's 63% gold and 37% copper. So 14K is not as pure as 24K. So therefore, is this a pure substance or a mixture? This is a mixture because you have two different types of atoms. So the answer is mixture. Is this homogeneous or is this heterogeneous? Because if you've seen a 14K ring, you can't really point out which parts are gold, which parts are copper, because it's a alloy. It's all blended together in a homogeneous sort of way. Okay. Baking soda. Baking soda is pure sodium bicarbonate, NaHCO3. And so that is just that one particular molecule. I mean, there's more than one atom, but it's the same molecule over and over and over. And so that is a pure substance. And is this homogeneous or heterogeneous? This is also homogeneous. Okay. Example of heterogeneous would be, say I were to put some sand in this container of baking soda. Then you would not just have more than one thing, because with the ring we had both copper and gold, but you can't really distinguish them. Where if I have something where you can physically separate the two of them, like a jar of different colored jelly beans or throwing sand into a container of baking soda, that's going to be heterogeneous. Hetero is indifferent. And so that's how you can tell what that is. Cookie, chips on a cookie, all kinds of things. Okay, intensive versus extensive properties. Intensive is what makes it what it is. Intensive, the important thing to remember is it doesn't matter how much of it you have. If I have a giant gold brick and a tiny gold nugget, they are going to have the same hardness, because that is part of what makes it what it is. So this is intensive. Volume. Volume is depending on how much you have. If it's an extensive property, it depends on how much of it you actually have. So how much is the weight? How much is the volume? That is extensive. Odor. Well, if something has a certain odor, it's going to have that same odor, whether you have a tiny bit of it or a bunch of it. So that is intensive. And density is also an intensive property. A small piece of gold is going to have the same density as a really big one. So all right, that is it. So good job sticking with me. And I hope that you are very successful in the test. If you have any questions, feel free to ask myself, or if you were in Miss Ford's class, ask Miss Ford. And that will conclude